Welcome to another solved problem on flitched or composite beams. The problem is stated as a compound beam 40 mm wide and 20 mm deep is formed by joining two rectangular bars, one of brass and the other of steel, each 40 mm wide and 10 mm deep. This beam is placed on two supports 1 meter apart and the brass bar is placed on the top of the steel bar. Determine the maximum load which can be applied at the center of the beam if the bars are firmly secured to each other throughout their length. Take Young's modulus for steel equal to 200 kN per millimeter square. Young's modulus for brass equal to 80 kN per millimeter square. Bending stress in steel equal to 112.5 megapascals and bending stress in brass equal to 75 megapascals. We first write the given data and the parameter to be found out. The composite beam cross-section is drawn next with dimensions and also the beam with the loading and supports. It is preferable to convert the beam composed of two different materials into an equivalent single material, either entirely of brass or entirely of steel, to make our calculations easier. Steel has a higher value of Young's modulus comparatively, and if we convert steel to brass, this will lead to an increase of dimensions in width of the equivalent beam made entirely of brass. Conversely, if we convert brass to steel, this will lead to a decrease of dimensions in width of the equivalent beam made entirely of steel. In either case, the factor of increase or decrease of dimensions compared to the existing ones for the corresponding materials depends on the value of the modular ratio, which is given by the ratio of Young's modulus for steel and brass, which comes to 200 over 80, that is 2.5. Let us select the equivalent beam made entirely from steel for our further calculations, as we would have to deal with smaller numbers. The maximum bending moment for a simply supported beam with a point load at the center is given by P times L over 4. We now proceed to find the vertical location of the centroid with respect to the base of the equivalent cross section. The vertical distance y bar is found to be 7.857 millimeters from the bottom edge. The section modulus ZS about the horizontal centroidal axis is found next as the area moment of inertia of steel about the axis over the distance of extreme fiber from the axis, that is Ys. Here there are two possible values of Ys, either considering the bottom edge or the top edge. We need to select the lower value of Ys since it shall lead to a higher value of section modulus, further leading to a reduced induced bending stress in the beam for a given maximum bending moment based on safety considerations. Hence, Ys equal to 7.587 millimeters is selected for the calculation of Zs. Now, the maximum bending moment induced is given by the product of the allowable bending strength in steel and the section modulus. We apply the values noting the consistency in the units used and hence find the value of the maximum allowable load as 921.81 newtons or 0.922 kilonewtons. In the next lecture, we shall look at the final solved problem on flitched or composite beams.